Hello, everyone. My name is Xavier-Marie. Viel. I work in the National Center for Grid Expertise in RT, France. Today I will present you work of a student, an intern student, whose subject was onshore wind farm generic models and sensitivity analysis methods for harmonic studies. Okay. So at first I will present you a few elements of context on the offshore and onshore wind farms overview in France. We'll present you harmonic amplification studies and methodology, and I will focus on onshore wind farms specificity. Then I will present you our onshore wind farm generic frequency model that we use for this study. And at last, I will present the sensitivity analysis methods and results. All right. So as you see in this map, we have quite a few offshore wind farm connection projects. We have the first AC connection, the first wind farms which are coming into our grid. So we divide it by tenders. So the first two tenders, we are connecting around 3 gigawatts of wind farm energy. So we will connect from 2022 to 2026 6 wind farms around 500 megawatts each. They are mainly located in the west coast of France. For the third tender, we will connect 600 megawatts wind farm, and after will come the DC connection projects. So we call them the tender 4 and 8. It's 2 wind farms of 1 gigawatt each. They will be connected in the Manche Sea. And we have also floating wind farms, mainly in the south of France, where the waters are where waters are deep. And we have small wind farms around 30 megawatts, which are demonstrators. And we will have bigger wind farms, floating wind farms, around 3 wind farms around 250 megawatts each. So you see that our projects are regularly coming into our transmission grid. Regarding onshore wind farms, we have already around 20 gigawatts of onshore wind farms connected in the grid. And around the majority of them are connected on the distribution grid. And the French government target in the 5 next years is to connect around 35 gigawatts. So we will still connect this kind of onshore wind farms. And RT, we develop and reinforce our transmission grid to connect wind farms directly on it or on the distribution grid. So we need to connect new substations, and these substations can be connected by long underground cables. And so, as you may know, our network is mainly inductive because of the overhead lines majority, and because of the machine, which are mostly inductive. And with long capacitive cables, we can have LC parallel resonances, so which can amplify the harmonic background. So the main objective of our studies is to estimate how the harmonic background voltage will be amplified by the connection. So our methodology, at first, we measure the harmonic voltage background in the substation, in the existing substation. After, we model in the EMTP, the TSO grid, the connection, and the customer, the wind farm grid. And we compute amplification with the parametric simulations. And after, if our computation show exceedances of our requirements, our voltage harmonic thresholds, we will design passive filters. So the amplification factors are calculated with an easy method. It's simply a voltage divider, and it depends only on the different impedances which are represented here. So the wind farm impedance and the cable and the transmission grid impedance, onshore transmission grid impedance. And we neglect for this kind of studies the wind farm emission, as we just want to focus on the harmonic background amplifications. So let us see the specific onshore wind farm topology when the producers are connected to the distribution grid. So here you have the transmission grid with the long 225 kV cable, and there, where is the mouse? You have here the transformer and the distribution network, which is composed of several producers, different producers, which are connected to this distribution grid. The main challenge is that they are not connected at the same time. RT prepares the connection, but the producer will come not at the same time. And as the producers are connected to the distribution grid, RT, the transmission grid, we don't have all the wind farm characteristics. So to estimate the amplification factors, we need generic models, and we need to carry out parametric simulations in order to calculate the amplification factors. Okay, now let us see the onshore wind farm generic frequency model. So as you know, we can connect mainly two different technologies of wind turbine generators, type 3 DFIG wind turbines and type 4 wind turbines. So these turbines are constituted with several elements. You have the converter, the inverters, the filters, and the transformers. So to model the inverters, we model them with analytic impedance, taking into account the control and several physical elements as the choke inductance. So we base our model on a paper which is highlighted here. This paper focused on the HVDC converter impedance, but we can use the same expression to model the wind turbine impedance. You got here the formula. As I said, we take into account the inner loop control, the outer loops control, but we assume that the PLL neglect the PLL for this expression because we assume that it won't affect the impedance after 100 hertz. We won't analyze the amplification before 100 hertz, so we don't need to model the PLL. In the literature, you can have these expressions taking into account the PLL, but we didn't use them. So we represented this impedance in EMTP with these components, which allow you to represent it with the transfer function. So we calculate the transfer function with the previous expression. So we represented the transformer, the equivalent collector grid of the producers, and well, you see that the topologies are quite different when we consider type 3 and type 4 producer. For type 3 wind turbine generator, it's the same expression that is used to model the impedance, but the equivalent inductance will consider all the physical components of the inductive generator. All right. So for the one wind farm, we can categorize the different parameters. We have the physical component parameters, which is the L shock, the equivalent inductance for type 3 wind turbines. We have the PWM filters reactive power. The reactive power will be used to design after the capacitance of the filters, which mainly impact the amplifications. We have also the wind turbine transformer series impedance and the length of the collector, the cable length of the collector grid. And we have also the converter control parameters. So the current loop, control time constant, the sample period of the control, and the different filters, voltage and current measurement filters, cutoff frequency. So now let's switch to the sensitivity analysis methods and results. So our general motivation for this kind of study is, well, it's not specific to harmonic studies, but we want to identify influence parameters. We want to provide a robustness to our studies conclusions. We also want to have a method to determine interactions between parameters. It's important for us. And also, we perform sensitivity analysis to optimize our parametric simulations. The idea is not to have too much simulations to run and to identify the influence parameters to avoid to do too much simulations, too many simulations. And specifically on this kind of study for harmonic factors estimation, when we connect the wind farms on the distribution grid, we want to answer these two questions. Have the wind farm parameters an influence when we compare it to the transmission grid parameters? And is it possible to estimate amplification trends with generic models and without having specific models? So the approach that we applied, at first we performed the sensitivity analysis with one aggregated wind farm with variable parameters, and we fixed the transmission grid parameters. I will present you. We use mainly two methods. Maurice and Sobol's methods. And for the first case, the idea was to see how we could we could carry a practical implementation with our simulation tools. After we carried out sensitivity analysis with the aggregated variable wind farm parameters and with variable transmission grid parameters, and at last we integrated all the complexity sensitivity analysis with multiple wind farms with variable parameters and variable transmission grid parameters. The Maurice method is a screening method, and it's quite efficient for a large number of input parameters. So the idea is that you will carry out one at a time variation of input parameters, and for this one at a time input variation of input parameters, you will calculate partial derivative, and you will calculate mean and standard deviation of this partial derivative. And after you can plot the standard deviation with the mean of these indicators, and you can easily categorize the inputs in 3 groups. So the first group of inputs, it's inputs that have negligible effects. The second group, they have linear effects, but without interaction between the inputs. And the last group here, these are parameters with nonlinear effects, and with or without interaction between the other inputs. So how we carry out this method? So we will at first generate parameters samples. We use the Python SALib library. You will give this library the different parameters. It will automatically sample it, and you will have your different sets of parameters given by this library. After we will run the parametric simulation with the parametric studio tool. I don't know if you are used to this tool, but it's another software coupled with the EMTP, which allows us to perform parametric simulation in parallel, to run simulation with multiple cores in parallel. And after, we will do the post-processing in Python, and it will also be done with the SALib tool. And we use internal scripts to calculate the amplifications to different frequencies, to different ranks, and we will compute the Maurice indexes. And so here we can see that we can for different harmonic ranks identify parameters that haven't not such an influence at the sample period, the cutoff frequency of current loop for this, for example, and we can identify parameters on which there is a huge influence. For example, the reactive power of the PWM filter, the length of the 20 kV cables, and also the equivalent inductance of the inverters. So it is interesting to plot these indexes with the regarding the different ranks, harmonic ranks. And we saw that the different parameters can have a huge influence for several frequency range, and others that they don't have so much influence. That's interesting for us. And what is also interesting in the use of the Salib pricing library is that you can group you can compute easily the indexes by grouping the parameters. So here you have the three main category of parameters in the wind farm. So the cable, the physical components, and the control parameters. And we can see that they have mostly the same influence, but we see that for our study we can focus mainly on these ranks because the sensitivity is higher on these ranks. So the benefits of this Morris method is that we can take into account a large number of inputs. The influential parameters can easily be determined, and there is not a need of high simulation to perform. We can compute these indexes with a low number of simulations. The drawbacks is that in Salib, they consider only numeric inputs, and it's quite difficult because some parameters can be categorical parameters. So it's quite too difficult to take into account this kind of parameters with the Morris method, and we regarding the interaction effects, you know that there are interactions, but you can't identify the parameters which are interacting. So the Sobol method is based on the standard deviation analysis, and it's relevant to identify the interaction between parameters. So you can decompose the variance with different terms, which represent the inner sensitivity of these parameters and the interaction with other parameters. So if we take a simple example with three variables, you will at first calculate the inner variance. So what is this term? You will fix one parameter with the symbol you choose, and you will vary all the other parameters, and you will calculate the mean of all these the outputs, and then you will take the variance of all these elements, and after you will calculate the interaction between two parameters. So it's V1, 2. So you take these two parameters, x1 and x2, you fix them to the different samples you choose, and you compute the variance, the mean and the variance of all these outputs, and you subtract the inner variance, and so on. And after, you can normalize these terms by dividing these indexes by the total variance of your outputs. Okay, so here you have represented this total sensitivity index regarding the different harmonics. So as we normalize it with the total variance, it's not anymore possible to compare the different ranks, because you will compute the amplification at each ranks and the variance will be different at each rank. So the main drawback of this method is that you can compare the different ranks, but it gives you more information of on the interactions. One other drawback of this is that it requires a higher number of simulation to determine the interactions between parameters. All right, so when we want to consider all the parameters for the wind farm and all the parameters of the transmission grid, it's quite difficult to manage it with parametric CDO and EMTP because you have to manage two different groups of parameters. So when you use aggregated equivalents to get an easier way to do the analysis, the sensitivity analysis, it leads to oversensitivity to wind farm parameters. So you will. The idea here is to build a generic wind farm Loci of the wind farm, and also a generic Loci of the transmission grid. And we will select randomly points in the different Loci. So we won't have a detailed overview of the different parameters, control parameters in the wind farms, but it will be easier to carry out the overall sensitivity analysis. So for that, we compute different Loci of different producers with random parameters, and after we connected them together in the same 20 kV bus bar, and we perform frequency scan to build this overall 80 megawatts Loci. And in this Loci, we add another parameter, which will be the rate of type 3 or type 4 wind turbine, which are connected to the grid. So here you can see what's the difference between an aggregated wind farm Loci and with versus multiple wind farms Loci, and we see that for multiple wind farms Loci, the Loci are much smaller. So it shows that our sensitivity to the multiple wind farms impedance will be smaller. So what we see here when we apply the Sobol method, you can see that the wind farm has a high influence in the above the 10th rank, and it can have a high influence also on the rank around rank 11th. And when we compute the multiple wind farms Loci, you can see that finally this influence is lower, and the amplification mainly depend on the RTE grid. And this is a good news for us, because when we compute our amplification factors, we can be mostly confident, because they depend only on the transmission grid parameters, and we can deal with these parameters because it's our grid, and it depends less on the wind farms parameter, which are unknown for us. So to conclude, we test several sensitivity analysis methods. We generated generic Loci, and this generic Loci can be reused for multiple projects. And now we need to structure our scripts to use them for other studies, like over voltage, transient over voltage studies, because these methods are not specific to harmonic studies, but they can be reused for all kind of studies. Thank you for your attention. Very much. Yeah. For the onshore wind farm, we use CP cables, which is not quite a good model because we don't have the frequency dependency. But for the long underground cable on the transmission grid, we use wideband models. But it's quite challenging to use them because we can't vary easily the length of this. So we are obliged to sample it manually and to select it randomly for different lengths. That's quite difficult. Thank you.